welcome to the Legends Symposium of Environmental Chemistry. This is part of the 236th National Meeting of the American Chemical Society. This is the second and last day of the symposium. We're here to recognize, to honor, to record for posterity people, individuals who have contributed to chemistry and have beneficially affected mankind. Each one of these individuals, if you think it through, have beneficially affected all of us. We all have a better quality of life because of each of these individuals. And it's not just we, me, or we, it's everybody on this planet. Welcome. I'd like to ask Susan to introduce Carrie.
So I'm very pleased to introduce our first legend of the day, Gary Hieftje, who is distinguished and chaired professor at the chemistry department and the School of Public and Environmental Affairs at Indiana University. Gary's highly recognized for developing new atomic instrumentation to measure metals and other pollutants in the environment. In fact, he has an atomic absorption technique named after him. Gary's received numerous awards for his research, including the IR 100 Award and the coveted ACS Chemical Instrumentation Award. Please join me in welcoming Gary Hieftje.
As I was saying, I'm delighted to be here, to be part of this symposium. I feel a bit like an interloper because I'm not really recognized as an environmental chemist. And in fact, when we go through the first couple of slides, I think that you'll see what I'm talking about. This is the title that I've used for the presentation, New Toys, Tools, and Techniques for Environmental Measurement, because my work tends to emphasize the development of new kinds of instrumentation and methods. And I think that that'll become clear as we go along here. I want to thank, first of all, Susan and, of course, Vic Tarosky for inviting me to be part of this session. Ron Heitz also, because I think that it was probably Ron who suggested my name in the first place. The ACS Division of Environmental Chemistry, and, of course, we're going to meet tonight at the Chemical Heritage Foundation. I want to thank all those people and groups. This is sort of a brief outline of the presentation, but I'll emphasize this last point. First of all, I'd like to define what a legend is. I don't know if anyone else has done this so far. I was part of 2 other sessions yesterday, so I couldn't be here. I apologize for that. I'll talk about some past legends from my own group and then hope what might be some future legends, and that's really what I'd like to emphasize. Legends aren't much good unless we can continue the legends, so I'll hope to outline for you some future legends that might develop. So first of all, what is a legend? I looked up a whole bunch of dictionary definitions. These are just a few of them, and really I think it's more appropriate if we just focus on one of them. That's the last one here. Read it for you. A tale or story that typically recounts great achievements that often reach heroic proportions. Such tales may be passed down for generations or describe contemporary events. They may be completely accurate, factually based, yet exaggerated, or entirely fictional. And I'll give you a really good example of a legend. Here's a legend. Gary Hieftje is a famous environmental scientist. That's about as good a legend, I think, as we could come up with. That's entirely fictional. As I say, I really probably don't belong in this symposium, but nonetheless, I'm honored to be counted among legends in some way. There are some legends at Indiana University, and I want to point them out first before I continue. John Hayes is a true legend from Indiana. John has recently retired from Woods Hole. He left Indiana a number of years ago, went to Woods Hole and to Harvard, and continues work in isotope ratio mass spectrometry. John's very well known for his work in environmental science, but also biogeochemistry. And he and Milos Novotny, jointly way back in the 1970s, developed the GC mass spectrometer that went on the Viking missions. Milos is also a legend. Milos is, of course, very famous for his work in capillary gas chromatography, supercritical fluid chromatography, detection methods for GC and liquid chromatography, and so on. Another legend at Indiana is I think we have one of the first schools of environmental science in the U.S. This was started in 1972, and as soon as it was started, I joined that school. So in that sense, I guess I am an environmental chemist. I've had a few students from the School of Environmental Affairs. Ron Heitz is really a legend, I think, in environmental science. Ron has been famous for many, many years in his work in GC mass spectrometry, looking at such things as dioxin, polybrominated diphenyl ethers. These are the flame retardants. And the discovery when fire began. I won't have time to go into that story, but if there is time at the end and you ask me a question, I'll be glad to recount that for you. But Ron really discovered, at least according to one manufacturer, when fire began. And finally, Phil Stevens, he's the latest addition in our School of Environmental Affairs. Phil's doing work in atmospheric science. So those are really the legends at Indiana. I could spend the whole time talking about them and their work. But let me describe very briefly for you the past legends that, if you want to call them that might have come from my group. This has already been mentioned, the Smith-Hieftje method for background correction and atomic absorption, still a commercial device offered by 3 different manufacturers. Fiber optic sensors for environmental monitoring analysis, that's been a very common theme in my research for the last 30 years or so. Miniature ICP systems, these are really found in most of the ICP emission spectrometers and in one ICP mass spectrometer that's now commercially made. The idea is to shrink the size of the ICP torch, and by shrinking the size of the torch, the system operates at lower power and low gas flow rates, so it's really smaller and more economical. We've also developed a radionuclide-based light source. This light source operates or derives its energy really from a radionuclide, typically strontium-90, but we've used other radionuclides as well. And each one of the radioactive disintegrations produces a little light flash, and that light flash is statistically on a 1 second to about 10 to the 5th year time scale very, very stable. So it can be used, for example, for environmental monitoring without having any required power. The only thing you need power for is any detection apparatus that you might have. ICP time-of-flight mass spectrometry, there are now 3 commercial systems, a 4th one to be soon introduced, and we're the first ones to do ICP time-of-flight mass spectrometry. And one of the later things is a source for ambient mass spectrometry. The idea there is that you put your sample, whatever it happens to be, an environmental sample of some kind, in front of the mass spectrometer, right in front of the source, and you get the mass spectrum, but a very simple mass spectrum. Basically, you get only the molecular ions. So it's a very simple mass spectrum, allowing us to do separation-free mass spectrometry determinations. So those perhaps might be some legends from the past, but as I said, I'd rather concentrate on the future. And these are some future legends that I'll talk about. I'll occupy the rest of my time talking about things that I hope are going to develop into legends. One is an array detector analytical mass spectrometer. We call it ATOMS. A solution cathode glow discharge that is really set up perfectly, I think, for elemental monitoring in environmental situations. And finally, a dual source time-of-flight mass spectrometer that can be useful for environmental and especially speciation analysis. The idea there is that speciation tells us not just which elements are present in a sample, but also what the nature of the chemistry of the elements might be, which anions might be bound to the metals, what the oxidation state of the metals might be, and so on. And of course, you'll agree, I hope, that those factors are extremely important for environmental monitoring, remediation, and so on. So let's jump to the first topic there, the array detector analytical mass spectrometer. And I'll try to make this a little bit entertaining. A 50-minute talk is about, it'll burn out any of my students, I can assure you of that. So I have to have a little bit of entertainment here and there. Now, the first thing is I think that in the next generation, we will find that virtually all commercial mass spectrometers will be simultaneous. And that's really the goal of the project I'm going to tell you about right now. And to give you an illustration of this, think about what happens in a scanning mass spectrometer. In a scanning mass spectrometer, you look at one mass-to-charge ratio at a time. You have to hop from mass to mass. It's sort of like looking at a photograph through a peephole. If you look at only one pixel at a time, you're missing all the rest of the photograph. That's not very good. But of course, if you spend enough time looking at all the different points on the photograph, you can get an impression of what the photograph is all about. The problem is if you have a movie. If you have a movie, of course, wherever you're looking, something else is happening elsewhere that you can't see. And that's, of course, what happens if you do, for example, GC mass spectrometry, because you have a continuously changing concentration profile. So it's more like looking at a movie. And I'll illustrate that for you, first of all. Here's just one little pixel of a movie. I don't know if you can see that it's a movie, but it actually is changing a little bit. And if you're looking at that, you're missing what's going on up here, but now you can't see what's going on in the first point. And if you look there, you, again, are losing all the information. So no matter where you look, you're going to miss out on a lot of the photograph. And if you didn't see all this, you'd really miss a lot, I think. There are, of course, some fundamental reasons why it's important also to do simultaneous detection. There's a multi-channel advantage. If you have a whole bunch of channels, let's say you have 100 channels, and you have to look at each one for the same amount of time, then you spend 1/100th of your time on each channel. And that means that your signal-to-noise ratio will drop by a factor of 10, the square root. So both precision and the limits of detection improve as the square root of the number of channels if you do a truly multi-channel or simultaneous detection. So that's fundamental. As I'll show you, you can also get better precision by means of ratioing if you measure things in a truly simultaneous fashion. Of course, you can analyze more samples per hour because you're looking at all the spectrum all the time. You get better time resolution for the same reason. And you can avoid something called spectral skew, which was defined originally, I think, by Chris Enke. The idea is here, and it's especially appropriate for GC or LC mass spectrometry, but also whenever you have any transient sample, anything that changes as a function of time. So here's, for example, a chromatographic trace, but it could be flow injection or a lot of other things. And let's imagine that whatever we're looking at here, whatever concentration is changing, has a very simple mass spectrum. 2 peaks, one yellow one purple one, at different mass to charge ratios. We'll just assume that they have the same amplitude. They have the same, if you will, isotope composition or concentration. Now, if we look on the beginning, the leading edge of this peak, we'll look first of all at the yellow peak, and then we'll look at the purple peak. But notice we look at the yellow peak at a lower concentration than the purple peak. That's what happens with the scanning system. So as a result, we're going to have this thing called spectral skew. That is, the yellow peak will appear to be artificially low compared to the purple peak. And of course, the opposite thing will happen on the downslope side. There, if we look at the yellow peak first, it'll be at a higher concentration than the purple peak, so the spectral skew will be opposite. Only if we look at both of the peaks at exactly the same moment in time, or fast enough compared to the speed of that transient, can we overcome this problem. So that's another reason why transient samples really should be measured by means of a simultaneous mass spectrometer. Well, this is the simultaneous mass spectrometer that we've developed. It's a Mattock-Herzog design system, so here's the electric sector, here's the magnetic sector, the slit is sitting right here, and all the rest of the front end is to enable it to be coupled to different ion sources. In particular, I'll talk about an inductively coupled plasma. We've used a whole bunch of different ion sources with this, but I'll talk about the ICP because I think that that's more useful in general for environmental samples. It's a fairly small mass spectrometer, only 80 centimeters long. That wasn't done because we wanted the system to be small, although that's a benefit. The important thing is that by having a small system, the mass to charges that are all brought to focus at the same time along this focal plane all can be, they can span a very broad mass range. So we can look at a fairly broad mass range over what's about a 3-inch focal plane over here. Now, I'd like to take you through a little tour of this device. So let's look at it in a little bit more detail, look at the ion optics in the front end and that sort of thing. But before I do that, I want to thank all the people involved in this. It's actually a multi-institution operation. We have people from Bonner Denton's lab. Here's Roger Spurline from Denton's lab. Here's Denton's head floating in the background because he didn't want a beer that day. These are 2 guys from my lab. Charles Baranaga is with Dave Coppenall at Pacific Northwest National Lab, and Greg Schilling also is still in my laboratory. So those are the guys who do the work. Let me take you on a tour through this device. Here's our ICP in the front end. We have then a differentially pumped interface. So we go from atmospheric pressure to 1 torr. There's then a skimmer. The skimmer goes to about 10 to the minus 3 torr. Then there's a conduction limiting orifice just upstream of this so-called equal optic. Here's a conduction limiting orifice going down to 10 to the minus 6 torr. Then we have some ion focusing optics, really just a double quadrupole, a DC quadrupole system that squeezes the beam down so it more efficiently passes through that entrance slit. Then the beam comes down through here. It'll pass through the electric sector, which bends the ions upward, of course, because of the electric field, separates them according to energy. Then they'll be refocused. You can see we get discharges in the spectrometer sometimes. That's just a glitch, actually, in the animation. We see that the blue beam here is a lighter one, and the green beam is a heavier one. So that shows us how the system operates. So we have different species impinging on this array detector right here. So now we have a multi-channel detector allowing us to measure all of those things at the same time. Now that's okay, but I'd like to take you on a little bit of a Disneyland tour of this thing. I even put some music in this if I crank up my... I don't know if you can hear this or not. Can you hear it? Hope you like Phil Collins. It just seemed to fit somehow. This shows the system in an animated form. It's really taken from a machining diagram. Here's the ICP. We're going to go right down the throat of the ICP, and we're going to be ionized. In fact, we'll see the ions flying from us in just a few minutes. There's a sampling cone going to the 1 torr region. I think Phil Collins fits, doesn't it, somehow? Then we go through an extraction optic, as I said, the 3rd stage aperture. I missed the skimmer. This quadrupole doublet, which shapes the beam again so it more efficiently goes through the entrance slit. We'll see coming up here in a moment. We'll lose some ions, of course, because the ions have a range of energy, so they aren't all exactly focused right, and the other ones are neutralized on the side of the entrance slit. Here we have this ion tunnel that brings the ions into the electrostatic sector. I should probably just shut up and listen to the music. It would be better. The ions are again bent, in this case, to the left in the electric sector, and then they'll be bent back to the right in the magnetic field. And remember, the blue ions were the lighter ones, so they'll be bent through a sharper angle in the magnetic sector. And once we get past this corner, we'll be able to see the array detector coming up. The blue ions you see are being bent in the sharper trajectory, so when they hit this array detector, they're detected this channel, the green one's over here, and the red one's right in the center. Makes you think students have too much time in their hands, doesn't it? The real key to this whole thing, the heart of it, is a multi-channel detector that was developed mostly by Bonner Denton and his group at the University of Arizona. It's really, really clever, I think. The idea is that it has a whole bunch of Faraday strips. I won't call them cups because they're really just little gold-plated surfaces on a substrate of some kind. We've used different substrates. The good thing about the Faraday strip detection is that it's free of thermionic emission and dynode statistics. These are the things that produce fluctuations in the output of an electron multiplier. But the bad thing is we get only one count per ion. Because we get only one count per ion, that means there's no amplification. We need really, really low noise. And this system, luckily, produces very low noise. Another nice thing is that if we want to look at biomolecules or really large molecules, there's no dependence on ion mass, since the Faraday strip detection simply is a charge collector. It doesn't depend on the kinetic energy of the ions. Another nice feature about this device is that it has continuous integration, and we can randomly access which mass to charges we want to look at. So we can look at a light mass and then a heavy mass, one at the middle, in any order that we wish, all along that focal plane. We also have the option of non-destructive or destructive readout. What that means is that if we have a very intense channel that is integrating rapidly, we can read the integral and then knock it back down to zero. That's the destructive readout, and then let the thing continue to integrate. Whereas a really weak channel that's integrating very, very slowly, we can let integrate for a longer period of time. So that extends our dynamic range and also allows us to read the same channel over and over again to get rid of any electronic reading noise that the electronics might produce. This shows the way the device works. So let me go back here just a minute. I want to show you that thing coming in. This is, for those of you who have taken electronics, it's really just an operational amplifier integrator. Of course, the engineers don't like such simple terms. They call it a capacitive transimpedance amplifier, but that's too big a mouthful. Let's just call this an operational amplifier integrator with two different capacitors in the feedback loop. So the idea is whenever an ion comes in here and hits that Faraday strip, that ion is integrated, basically. The charge is integrated. So it produces a voltage output, a voltage step, if you will, at the output of the operational amplifier integrator. And every time an ion hits, we get a little bit larger integral built up there. A nice thing is that the magnitude of that integral, the output voltage really, is not only equal to the charge, it is the time integral of the current, but also it's inversely proportional to the size of these capacitors. So the smaller the capacitors are, the larger the voltage is going to be. In fact, if we have two different capacitors, one of which can be switched in and one of which and can be switched out if we wish, we can actually get two different levels of amplification independently from channel to channel. The smaller one gives us 16 microvolts for each elementary charge, each ion really, each singly charged ion. And if we put the larger capacitor in parallel with the smaller one, we get 0.16 microvolts. So we actually have per charge. So that means we have a range here of 100, factor of 100, from one channel to the next. Now each of these channels can be read out by a multiplexer, again in any order that we wish. So every channel has its own operational amplifier integrator just like this. If the signal is getting too large, the computer simply resets the system by means of a field effect transistor up here. So it allows us the option again of doing either destructive or non-destructive readout and looking at any channel in any order that we wish. The most recent generation that I'll talk about here has 45 micrometer fingers. The newest one that we're working on right now that's in our laboratory has only 14.5 micrometer fingers to give us even better resolution. And on the one that I'll talk about here today, we have 128 channels. The newest one has 512 channels. That's the one that the students are working on right now. With this old device, the 128 channel system, it takes 1 millisecond for a spectrum. The new one takes a half millisecond. So we have many more channels, 4 times the channels, but much more speed. Actually, we get, as I said, a spectrum at half a millisecond, 2,000 spectra per second, fast enough for any GC trace. This shows the system, the 128 system installed in our mass spectrometer. Show you just some figures of merit very briefly, and then I'll give you an example of how this could be useful. These are some detection limits, and this line, this little dotted line here, is 1 part per trillion. So as you can see, most elements, except the ones we have chromium and vanadium, these are contamination peaks, actually, because we have been ablating our stainless steel, unfortunately. But these, notice, are well, well below a part per trillion. In fact, they're down in some cases in the single part per quadrillion level. So we really get very good detection limits with this system. Another thing that's important I mentioned before, and that's that if we can measure things in a truly simultaneous fashion, we can overcome what I'll call multiplicative noise, or maybe we could call it correlated noise. The idea behind this is that if we have two channels that are fluctuating together, and they will probably with an ICP source because of flutter in the tail flame and changes in the nebulizer, the sprayer output, and that sort of thing, what will happen is that the two traces will really track each other in time, as we see in this simultaneous measurement. But if we use the scanning system, we'll be looking at one peak a little bit later than the other peak. And if we do that, we're going to have this kind of a situation where the two traces are offset. Well, of course, if we divide this trace for silver 107 by this trace for silver 109, we should get rid of that multiplicative fluctuation, that correlated fluctuation. But up here, we won't have that, because if we don't measure the things in a truly simultaneous fashion, when one is high, the other one might not be high, and so on. So the difference is really pretty dramatic if we do the ratio. If we have the simultaneous ratio, we're getting, in this case, 0.015% relative standard deviation. For the scanning approach, we get 0.65%. Really pretty different. And in fact, it turns out that this is limited, this precision is limited by the rate at which, or the total count of ions that we collect. If we have a constant flux going into the system, what we find is that the precision gets better and better, improves, as the square root of the integration time. So this is a log-log scale and has a slope of -1/2. Another nice thing about this approach is that because it's an analog detection system, we don't have to worry about two pulses piling up, two ions hitting at virtually the same time and losing the ions. If we have two ions hitting at the same time, they just produce twice the integral. So what that means is that we can increase the concentration going from, say, 10 parts per billion, the red peaks here, red dots, to 1 part per million, a factor of 100 increase, and we get an improvement in precision for a given integration time equal to the square root of that ratio. So we have a factor of 100 different in concentration. That gives us a factor of 10 better precision for a given integration time. And what we see here then is that if we go down to reasonable times here, for example, if we go down to 3 minutes, we can get 0.007% relative standard deviation. That's pretty darn good for an ICP. That's competitive with the best that you'll find in commercial systems. One of the other things that I mentioned is that this device has the ability to do non-destructive readout. So if a channel gets too intense, we simply destructively read that out and then let it continue to integrate. And that gives us a very broad dynamic range. This is 7 orders of magnitude. The new one that we just installed, the 512 channel unit, has 8 orders of magnitude, 10 to the 8th dynamic range. So it's pretty good. Now, there are a lot of examples that I could cite of where speed and simultaneous measurement really make a difference. If we want to do high precision isotope ratios, as I indicated, optimal internal standardization, which is really exemplified by high precision isotope ratios. Situations where the signal shape is critical, such as flow injection or carbon furnace vaporization. LC, GC, or capillary electrophoresis, where we have time varying signals. If we modulate the source, or fast transients, and I'll use laser ablation as an example. Now, a lot of people are using laser ablation, especially with ICP-MS these days, but I always try to caution them. In fact, we have a sign hanging on our instrumentation that says this: do not look into laser with remaining eye. Hope that my students pay attention to that. This shows you the kind of problems that you have when you use laser ablation. These are individual laser pulses, and we're simply looking at the chromium-52 peak. And what we find is that because of changes in the albedo, that is the sort of reflectivity of the surface of the sample, changes in laser intensity and that sort of thing, we get a lot of fluctuation. In fact, depending on the element, the fluctuation can really be very large, up to 20%, 21% in this case for tungsten. Some are a little bit smaller. But if we measure 2 peaks at the same time, remember, we can overcome those fluctuations. Because if more of the sample is ablated and we take ratios, those ratios should be pertinent no matter whether more or less of the sample is ablated. And in fact, that's what we find. If we operate that laser then in a rapidly pulsed fashion, 10 pulses per second, we see that the traces fluctuate like crazy. Those are 2 different molybdenum isotopes, but the ratio really turns out to be pretty constant. The ratio comes out to be something like 0.02% RSD. Some limits of detection, I don't want to emphasize this too much, but the best limits of detection we got here with laser ablation are for lead, and in terms of concentration, that is parts per billion in the solid, about 9 parts per billion. In terms of femtograms, about 46 femtograms. These are the worst detection limits that we got, and those are for strontium. What we can do with laser ablation is if you have an environmental sample that is spatially heterogeneous, or for example you have a sampling piece of filter paper that's collected atmospheric particulates, and you want to look at one particulate, you can do that. Just look at one particulate at a time. Or if you want to look even into a particulate, you can ablate just the surface layers of the particulate and drill down through it. And that's what we're doing right here. We're drilling down through, in this case, a NIST standard sample. It's copper and brass. And what we find going from 0 here, which is the first laser pulse, 400 laser pulses, 800, 1200, and so on, is that we're drilling down through the sample. So we find that there's a protective layer of chromium on the top. Then we're looking at the copper here in this particular spectral window. First the copper on the surface, and then the copper that's part of the brass, and then it turns out there's a steel substrate. And if we really look at this carefully, slow the pulse rate down, here's the kind of thing we can get. Pulse and pulse and pulse. We get about 4 to 5 nanometers depth erosion per pulse. We can get fantastic spatial resolution with this device. Okay, that's enough on that atoms. I'm going to stop and ask if you have a question on atoms before I proceed. Besides, that way I can take a drink. Any questions? Okay, on to the solution cathode glow discharge for environmental analysis. The guys who are involved in this deeply are Mike Webb, who's now a postdoc at Tufts, and Steve Ray, who's still back in Indiana slaving away on this piece of equipment. The real problem that we faced, and that, of course, you'll face, is that if you want to do field measurements in the environment, using an ICP is not a very practical option. We've got a lot of gas that the thing consumes, 15 liters per minute, sometimes even more than that. It's a very large instrument, so wheeling it around is not very convenient. You need a long power cord because it takes on the order of 2 to 3 kilowatts, actually, for the total instrument power. So it's not a very convenient option. Instead, we've turned to this device that we've developed in our lab that we call a solution cathode glow discharge. The solution cathode glow discharge operates in the open atmosphere. It doesn't require any flowing gases of any kind. All it takes is a little bit of a pump to pump the solution. Here's the idea. What we have here, if you look at this cartoon over on the side, is that solution comes up from the bottom, then the solution overflows a little capillary that you can see down here. So when the solution overflows the capillary, it makes electrical contact with a waste solution that spills out of the capillary. That then becomes the cathode of our discharge just by having another electrode sitting over here. So that electrode is the cathode, the negative electrode of the discharge. So the solution becomes then negatively charged, so a remote positively charged electrode brought to a few hundred volts produces a discharge. It's actually a glow discharge, but at atmospheric pressure, between that solution, directly between the solution and the counter electrode. So what that means is that we get cathodic sputtering from the surface of the solution. That means ion bombardment releases species from the solution. They're then neutralized because of a lot of electrons present in that discharge, and they're excited. So we get atomic emission from this system directly. It means that the atomic emission can very easily be imaged by means of a simple lens onto a monochromator and detector. We're using only a 0.25 meter monochromator, a little tiny thing. We've also used ocean optics spectrometers for this, the kind that fit right into your computer. Now there's some complications. If we have this discharge going on here, oh yes, I wanted to show you, I wanted to show you what goes on in this cathode. Remember that this electrode is negative. If we go over here, the negative connection is really made here at this graphite electrode. Other people have tried to do the same kind of thing, but what happens is they get hydrogen evolution over here at this electrode, and as a result, that destabilizes the discharge. Our hydrogen evolution occurs over here, which is remote from the discharge, and in fact is blocked by means of a simple divider that we put into the system. Let me show you what this device looks like, by the way, photographically. It's up here. This is the way it looks. And you can see here that there's a very bright emission, in this case from sodium, which is present in the solution. So the liquid comes up from the bottom, spills over the top, and makes the electrical contact to this pool of waste solution in the bottom. Generally speaking, the kind of figures of merit we get are detection limits on the order of tens of parts per billion for this. This is a large system, by the way, and precision on the order of about 1% when the concentrations are about a part per million. And the linear range is about 3 to 5 orders of magnitude. Not too bad for environmental measurements. No flowing gas, only about 1 to 2 to maybe 3 milliliters per minute of sample solution. But we've tried to improve on that. One of the things we've tried to do is to find out just how bad the interferences might be. A number of you have done atomic absorption or maybe atomic emission with an air acetylene flame, and you might remember the so-called ionization interference. if we increase the magnesium concentration here and look at the signal from the magnesium, but divide the signal in by the concentration, that is, we're looking at basically the sensitivity for magnesium, what we find is at first, when we add the first increment of magnesium, some of it ionizes because of the high temperature of the flame. What that means then is that only a fraction of our magnesium is in the free atomic state, so we get a lower signal. Some of it is in the form of ions and gives us a different emission signal, so we don't see it. As we add more and more magnesium, what happens is that the number of magnesium ions and electrons that are produced go up, and the electrons that are liberated shifts this equilibrium back to the left. So what that means is that the sensitivity, the signal we get per increment in concentration of magnesium, gets higher and higher. But in this particular discharge, we don't have that behavior. We have a relatively constant signal, and that's because there are so many more electrons. We've done the fundamental measurements here. A flame, such as an acetylene flame, contains about 10 to the 10th electrons per cubic centimeter. Sounds like a lot, but the ICP contains 10 to the 15th. So does this new discharge, about 10 to the 15th electrons. That means that there are so many electrons already present that virtually all of the magnesium is in the free atomic state. So added magnesium doesn't change the sensitivity. Another thing that we've looked at is the so-called phosphate interference. This is a matrix interference. Again, you're probably used to seeing in an atomic absorption. If you add, for example, phosphate to a calcium-containing solution, the signal you get from calcium drops very quickly. And the reason that drops very quickly is because the calcium is bound as a calcium pyrophosphate species. This is really not the right formula. It's a calcium pyrophosphate species that doesn't vaporize very efficiently. Now, the system that we have also suffers a slight loss in signal, but we can add lanthanum as what's called a releasing agent, just as you do in atomic absorption, and we get 99 plus or minus 2% recovery under those conditions. So there are some interferences here, but they're very easily controlled. We then turn to a different kind of system, a miniature solution cathode glow discharge, and our reasoning was very simple. If we use the same power, we didn't want to increase the power because that would make it inconvenient from the standpoint of a field system, we get a higher power density. So we made the distance between the solution and the electrode a little bit smaller. That changed the characteristics of the discharge in ways we didn't like. So instead, we simply narrowed the diameter of that capillary from 2.5 to about 1 millimeter. It gives us 5 times higher power density, and it also reduces the solution flow rate to about 2.5 milliliters per minute, much lower. And here's the way the system looks. In the dark, it looks like this. We get that same glow from sodium. Notice that the capillary in this case is only 1.1 millimeters in diameter. In this case, we have a 3 millimeter gap between the two electrodes. Here you can see perhaps more clearly that there's a solution overflow, and here's that bath of waste solution. We've used different counter electrodes. They seem not to be very important in their composition because they aren't really eroded. This particular one is tungsten. In fact, you can see the coating of tungsten oxide, but we use titanium and stainless steel and all kinds of stuff. So that's not very important. Let's now compare the detection limits that we got originally with the larger solution cathode glow discharge, the miniature solution cathode glow discharge, and ICP, atomic emission. These are taken from the manufacturer's literature. Forgetting for just a moment about the solution cathode glow discharge that we started with, look at the comparison here between the miniature solution cathode glow discharge and the ICP. Roughly equal, roughly equal, roughly equal, nearly equal, better, even better, and far better for the alkali metals. And that's because we don't have most of our species ionized in this discharge. It has a lower ionization temperature. So for things like the alkali metals, easily ionized elements, we get much, much better. These are in terms of parts per billion, so that's 60 and 20 parts per trillion detection limits for those species. So the detection limits here are really equal to what we get with an ICP. But with a system that doesn't take any gas flow, that has modest interferences, and that can be really carried in a small suitcase. Very simple device. Show you one other application here, and that's how well this device works with flow injection. If we employ flow injection with this very tiny capillary, remember it's only 1.1 millimeters in diameter, the transients become only 0.7 seconds long. Look at how reproducible they are. We get an area relative standard deviation of about 0.8%. We get very good detection limits that I'll show you, but notice that at 0.7 seconds, full width and half maximum, we can get more than 3,000 samples per hour analyzed. In this case, we're looking at the same sample over and over again, but that wouldn't be necessary, of course. Lastly, the detection limits in terms of what we get with flow injection. We can express those either in terms of parts per billion, that is solution concentrations, or in terms of absolute mass, and these are the relative standard deviations that we get. And notice that in terms of part per billion, again, for the alkali metals, we're down below a part per billion in the part per trillion regime. We're down below we're down below 1 picogram for the absolute mass for those. And of course, as I said before, we don't get quite as good a sensitivity for some of the other species. We still get very good sensitivity even for the worst of the elements here, which in this case is mercury. Notice also that we're down in the single digits in terms of RSD, so sort of 1% RSD, until we get things that are near the detection limit. In this case, we are using, as you see down here, the mercury RSD gets as good as 2.2% if we have a higher concentration. But in this case, we have only 500 parts per billion that we're introducing, and the detection limit for mercury was only 270. So we're only two times above the detection limit. And that's why the precision is no better than it is in this case. Any questions on that? No? Okay. I'll launch ahead then. The dual source time of flight mass spectrometer for environmental speciation and metallomic analysis. Metallomics is a new field defined by a bioinorganic chemist named R.J.P. Williams. And the idea behind it is to look at metals in all kinds of biological systems. But these are biological systems that also can be single-celled organisms that are present in environmental samples. The important thing is that in many cases we want not just to get information about the metallic composition of the sample, but also about the speciation of the metals. As I indicated before, what the chemical nature of those elements might be. Because the chemical nature, as I'll remind you, affects the difficulty of remediation and a whole bunch of other things. The people involved in this are Dwayne Rogers, who's still at Indiana, and Steve Ray, the same guy I showed you before. This is a nice quote. I think it pertains to this whole thing. Mike Dunn once said, there are 3 kinds of scientists, those who can count and those who can't. I'll let you think about that for a moment. This is the way speciation is usually done. Not always. There are different ways of doing it, but this is a common way. The idea is that we'll start with our sample, take an aliquot of it, perform a separation to get the speciation. So if we have different chromium, for example, different species of chromium, chromium-3, chromium-6, we'll separate them perhaps by means of ion exchange chromatography. And once that happens, we'll then feed them into an ICP mass spec to give us elemental information, isotopic information, and quantitative information. So the ICP provides us with a bunch of benefits: high sensitivity, elemental and isotopic concentrations. But the nice thing is it's species independent. No matter whether the chromium is present as 3 or 6, or whether arsenic is present as an organo-arsenic compound, or metallic, and not metallic, as inorganic arsenic, we're going to get that information. But that kind of loses some of the speciation because we get some of the speciation here, but we have to worry about it changing. So often what people are doing now is to perform a second step. Sometimes they'll eliminate this separation, but they'll go from a sample to electrospray ionization to the mass spectrometer, because with that type of approach, they can get structural information and information in general about the molecules. So they get the molecular ion mass, and if they wish, some fragmentation or structural details. That will then give them a more unambiguous idea of what the speciation of the samples might be. But that's a complicated and cumbersome business. 2 different analyses, 2 different separation schemes, 2 different steps. Takes a lot more time and a lot more sample. So what some people have started doing is they've combined the separation steps, and they go into both an electrospray source for ESI mass spec and to an ICP source for ICP mass spec. We think even that is inefficient. So what we've done is to go to the next step, and that's that we have one time-of-flight mass spectrometer that accepts the ions from both the ICP and the electrospray source exactly at the same time. So if there are 2 peaks coming out of the separation system, we don't have to worry about misidentifying those peaks. If you have a complicated environmental sample with a lot of peaks, there's a chance that the ICP source will produce a mass spectrum for this peak and this peak that are slightly shifted from the mass spectra from the electrospray source, if you have 2 different systems. With our system, they're taken at exactly the same moment in time, so we don't have that time shift. So we don't have to worry about misidentifying this peak with that one. Excuse me. So this is our approach. As I said, we have a single separation step, 2 different sources, but the same mass spectrometer. So we get all the information that I mentioned before, but all at the same time. In addition, if we restrict the amount of solution that goes into the electrospray source and ICP source, we can often collect an aliquot for further characterization if we wish. And here's the basis of the idea. How many people are experts in time-of-flight mass spec? Okay, one. Not many. Okay, I'll give you a very quick tutorial about time-of-flight mass spec. It's one of the oldest kinds of mass spec. Started about 1948, as a matter of fact, a long time ago. So long ago, even I don't remember it. That's the amazing thing. Very simple device, 2 electrodes, a very fast detector, and basically an evacuated sewer pipe. It's a very simple device indeed. So the idea behind this in the orthogonal acceleration approach is that the ions come in from the bottom, as we see here. The ions fly in from the bottom, and then we put a voltage between those 2 electrodes. So when we put a voltage between those 2 electrodes, let's assume for simplicity that all the ions are singly charged, as I've shown here. When we put a voltage between those 2 electrodes, what happens is that we produce a kinetic energy. We impart a kinetic energy to every one of those ions equal to that voltage times the charge that the ions contain. So if they happen to be doubly charged, they'll get twice the kinetic energy. What that means is that all the ions basically have the same kinetic energy, and because they all have the same kinetic energy, they all have the same 1/2 mv squared, which is kinetic energy, we all know. Therefore, the ions of lower mass have higher velocity, and they reach the end of the racetrack first. So the lighter ions hit the detector first, heavier ions later, even heavier ions later yet. So the time-dependent output of the detector is, in fact, the mass spectrum. Very, very simple. And in fact, we can relate all these parameters quite easily. The flight time for any particular ion, say this one, is equal to the length of the flight tube times something proportional to the square root of the mass to charge ratio. And of course, that voltage comes in here as well. So we can get the mass spectrum directly from this device. Now, what many people fail to think about, unless you build these things, which we happen to do, is that the initial kinetic energy that the ions have flying into this zone is not lost. They still have that kinetic energy. So even though we accelerate them at a right angle, they don't travel at exactly a right angle. They travel at a slight angle upward. So the original kinetic energy, as I said, is retained. The ions continue in that direction, but now they're also shot at a right angle, so they come out here at a slight angle. And that's the secret, then, of using more than one ion source at the same time. If, for example, we use, in this case, we have a simian simulation of the system. Here's the whole mass spectrometer, a time-of-flight mass spectrometer. Here's our ion source region. So the ions come in from the bottom as we see them flying along here. When the ions come in from the bottom, they actually leave at a slight angle, and that slight angle then carries them through an ion mirror called a reflectron, and then back to the detector. So it's a simple extension, then, of that reasoning to say, why don't we just put a second source going in the other direction? So one source will come down from here, one source from the bottom. So let's say, for example, we send ions from the ICP from the top. Those are the blue ions. They'll go through the reflectron and hit a detector sitting here. Ions from the electrospray source come in from the bottom. They hit a detector over there. Or, in fact, we could have an ion source from the top and from the back. In fact, we could even have a pinwheel of ion sources if we want not just 2 or 3 or 4. We could have virtually as many as we want. So that's the concept behind it. We've done a lot of simian modeling. We've done a lot of building. This is an example of the kind of thing that we do at Indiana. We have a marvelous machine shop, 7, actually now 8 full-time machinists, 2 of whom work in my group almost all the time. It's really fun. But it costs a fortune. It costs us $7 an hour. Just hate that. Isn't that terrible? Anyway, this is the device that the machine shop made. Steve Ray and Dwayne also made part of it. This is looking at it from the ICP side. The ICP would be right here, but we took it out for this particular photograph so you could see it. One thing I wanted to point out is that the ICP detector is really over here. The electrospray source comes in from the back. I'll show you that. But it's set downward just a little bit from the ICP channel. So the electrospray detector sits here. So when the 2 ion beams come in, one is above the other, so they don't interact. We're going to try the interaction to see if there are any benefits or liabilities, but we haven't yet done that. But so far, anyway, they're offset vertically from each other. And this is the kind of behavior we get. For the ICP time-of-flight system, this is a multi-element solution, standard multi-element solution, going over the whole mass range up here in the high mass range all the way up to uranium. We can see everything. We have monster peaks caused by such things as argon and argon oxide, a lot of other things. We have ways of getting rid of those. We call those deflection windows. And I could get into that in detail with anyone who's interested. I think I clicked this, but, oh, there we go, okay. Just to show you that it works fairly well, we have a bit of noise in the background in this case, but this is for selenium, and we're getting peaks that correspond nicely to the isotope ratio. These are ICP peaks that are way in the high mass range where the resolution is most difficult. Notice that we have about 1500 resolving power, nice baseline resolution between three of the lead isotopes, and also I'll show you one with bismuth in a little while. This shows the system from the electrospray side. This is our electrospray source. We've made that ourselves as well. And frankly, it's not as good as commercial electrospray sources. We have to buy a commercial one and put it on here. But this shows the kind of behavior we're getting with the electrospray source. In this case, we have a little peptide, leucine and kephalin, and you can see it's a fairly small one, about 550 sort of molecular weight. A bunch of solvent peaks. There's a supporting electrolyte. But the resolving power isn't too bad. We should be a factor of at least 5 from that. I'm sure we can. Here we see the whole system in its photographic glory. Here is the ICP. The ICP ion optics connections are in here. The ICP detectors over there. The electrospray source is on the far side. Shows the simultaneous measurement of the big monster molecule, myoglobin, and the ICP. How am I doing for time here? It's supposed to be in 5 minutes. Okay, great. Then I think, yeah, I have time. I'm going to tell you a little side tale. Myoglobin, you know where myoglobin comes from, or where it's in your body? It's in the muscle tissue. It's the thing that allows you to run for long distances. And one of my colleagues, his name is Frank Gerd, was a protein biochemist. A long time ago, he wanted to characterize a protein. In those days, it was a hard job. He had old gravity-fed ion exchange columns and that sort of thing. He was using myoglobin. He'd get in hundreds of pounds of whale myoglobin. Whales have tons of myoglobin. So he'd have these big, ugly, smelly things full of myoglobin. And they would use something that was called menhydrin, which would stain the amino acids when they came out of the column. Well, those guys would have floods all the time. They'd have these columns. They'd have overflows from the columns. They'd have overflows from distillation things. And my students were always mopping up the floor. So one morning I came in, and one guy was wiping down the wall because there's another flood. Turns out it wasn't water. It was menhydrin. This guy had blue arms all the way up to his shoulders for about 6 weeks. He wasn't very happy. At any rate, this is not stained. This is simply old myoglobin. The ICP channel looks at the iron in the myoglobin. The electrospray channel looks at all those different charge states of myoglobin. This is another molecule of interest, cyanocobalamin. Anyone know what that is? Better have it. Vitamin B12. That's right, vitamin B12. So here we see cobalt, which you'd expect to see in cyanocobalamin. Doesn't kind of make sense. And what the heck is this? It's labeled germanium. Look at that. The isotope pattern is there. Why they put germanium in vitamin B12 capsules, I have no idea, but it's there. Here's the molecular ion in the electrospray channel, so that works fairly well. If we use the ICP, we can very easily do a standard additions analysis, and by means of standard additions extrapolation, we get 21 parts per billion. That corresponds to 509 micrograms for the sample size we used, and that compares nicely to what the manufacturer says. So here's the state-of-the-art for this system, electrospray and ICP channels. Resolving power isn't quite as good as we'd like. We know it's going to get a little bit better. Same way with the detection limits. We're not in too bad a shape. We have, for the ICP system, about 100 parts per trillion. We know we can get down to less than a part per trillion. We've done it before. Dynamic range, we have about an order of magnitude to go. Same way with the electrospray source. A lot of work has yet to be done. I won't spend time talking about that, but we need better sensitivity. We're going to introduce transient signals, especially from chromatographs. We're going to have a collision cell, really a quadrupole collision cell on the front end of the system, and that should give us better detection limits and better resolution. And ion trap will go on the front end, and as I said, we're going to interface it to a separation system. So I better take word here from Will Rogers. Will Rogers said, never miss a good chance to shut up. So I'll do exactly that. But thank again, Vic and Susan, for inviting me. Thank you for attending. And if there's time, I'll be glad to answer any questions. Thanks.